Good morning. My name is Shubh, and I'm a PhD student in the Navigation and Autonomous Systems Lab at Stanford. Today, I will be presenting on some of our recent efforts towards designing deep neural networks for sequential GNSS positioning. GNSS positioning has conventionally relied on model-based approaches, which have existed for decades. These approaches rely on carefully studied and constructed models of various aspects of the navigation problem. For example, models of the satellite and receiver clocks that incorporate ionospheric and tropospheric delays, as well as clock stabilities, or models of the measurement error that include bias and stochastic errors, models of the navigation signal that utilize both pseudorange geometries as well as motions of the satellites, and models of the receiver motion that utilize vehicle dynamics as well as measurements from additional sensors such as velocity. While these model-based approaches usually perform well in the operating conditions that they're designed for, a limitation is that they tend to have poor performance when these conditions deviate significantly from the model. To address this limitation, learning-based approaches have been an active area of research in recent years. Instead of relying on carefully constructed models, these learning-based approaches instead use data to construct data-driven models of measurements and position. There are two main categories of these approaches that have existed in recent years. One is measurement domain models, which aim to determine the satellite visibility or uncertainty, or correct for pseudo-range errors, or classify the operating conditions in which the measurements are present. The other category is position domain models, which aim to determine the receiver's position either within a discretized grid, or as a correction to an initial position, or as a part of a time sequence. A limitation of learning-based approaches, however, is that they require large quantities of data, training time, as well as memory. So in summary, both model and learning-based approaches have their advantages and disadvantages. Model-based approaches leverage known structures of the GNSS measurements, have no data requirements, and have small memory footprints, while learning-based approaches learn this measurement structure from scratch, which often leads to large training times. They require large amounts of data to train, as well as memory and computation is expensive, these approaches. Advantages of learning-based approaches are that they tend to achieve good performance even when the structure of these measurements in different environments is unknown, and they can rather easily specialize to these different operating conditions by looking at data. While model-based approaches require knowledge of the measurement structure to achieve good performance, and they often might even require redesigning the approach if the operating conditions change significantly. So looking at both of the advantages from model-based and learning-based approaches, we conclude that these approaches are both useful in GNSS positioning in their own rights. Model-based approaches can utilize the known structure of the navigation signals, such as in the geometry matrix or as in the models of the expected measurement, while learning-based approaches can infer data-driven properties of the environment, such as environment-specific bias errors or satellite visibilities, or corrections to be applied to these measurements. Therefore, it makes sense to try and combine these two approaches and overcome their individual shortcomings. So in this work, we design a hybrid learning-based approach that builds on existing models that are utilized in model-based approaches. Instead of learning the measurement structure from scratch, our approach starts from the geometry matrix and models of the expected measurements and augments them with components and corrections that are learned using data. Then these hybrid models are then utilized in determining a final position that contains both model-based and data-driven components. The intuition behind this approach is that the data-driven components, augmented with these model-based components, adapt these underlying model-based approaches to different environments where the original models may not fully apply. So this proposed hybrid approach is also advantageous over other learning-based approaches by being more efficient in terms of data and in terms of memory. To visualize why that is the case, we look at the optimization space that the existing learning-based approaches operate in. And as the size of this optimization space is reduced, the approaches get more data and memory efficient because they rely on fewer parameters that need to be optimized. In this view, fully connected neural networks are optimized over the entirety of the differentiable function space and therefore are inefficient and require several parameters. Uh, the other approach, which is deep GNSS that we proposed in a previous work, is somewhat more efficient because it optimizes in a smaller space, which is the intersection of permutation invariant functions with functions that support variable-sized inputs. And therefore, this approach requires fewer parameters over the fully connected neural networks. Compared to both these learning-based approaches, our current approach optimizes within the smallest space, which is the function space of least squares optimization problems, and requires the smallest number of parameters and is the most data and memory efficient. Here are our contributions. We explored a novel hybrid learning-based approach for GNSS positioning that builds on model-based approaches to increase the positioning accuracy in the different operating conditions over existing model-based approaches and improve the data and memory efficiency over learning-based approaches. Our designed approach can combine information from GNSS measurements that are also obtained at different times and therefore perform sequential positioning. And finally, we validated the efficacy of our proposed approach on simulated GNSS measurements that contain varying bias errors. Here is a summary of the existing learning-based approaches for GNSS positioning. We have compared them on the criteria of producing position domain outputs, learning interactions both across satellites and across time, being invariant to the input size and order, and whether they build on existing model-based GNSS positioning approaches. To the best of our knowledge, ours is the first approach that meets all of these criteria. The outline for the rest of the talk is as follows. I will first go over our framework for hybrid learning-based sequential GNSS positioning, where I will go over the individual feature extraction steps, our hybrid learning-based architecture, and how we extend that to the sequential architecture. And then I will go over the experiments and summarize. Here is a high-level visualization of our framework for hybrid learning-based sequential GNSS positioning. Starting from an initial position, clock bias, and GNSS measurements, we first extract features, which are then processed by a learned hybrid module. And the output from this hybrid module is then integrated by a long short-term memory that combines the sequential information to produce the final corrected position. Both the hybrid module and the LSTM module are learned together in an end-to-end fashion. First, I will talk more about the feature extraction. Our feature extraction module is based on linearized pseudorange model features which were proposed in our previous work. Starting from the initial position and clock bias, we combine the satellite positions to calculate expected pseudorange and line of sight vectors. Then add errors from the known models of ionosphere, tropospheric errors, relativistic errors, earth rotation, and clock stability to produce an expected GNSS pseudoranges and difference them with the measured values of the pseudoranges to produce residuals. These GNSS residuals and line of sight vectors are then used as features for the subsequent module. Next, I will go over our hybrid module. The hybrid module, which we call High Dimensional Least Squares Network, or HDLS-Net, operates on the GNSS features from the previous module and to determine an overall position correction. First, we apply a learned high dimensional least squares operation on these features, which I'll talk about in more detail next, to produce an operating context as well as a model-based position correction. Both of these outputs are then passed to a fully connected network to produce a learned value of the correction, which is combined with the model-based correction to get the overall position correction. Next, I will talk about this learned higher dimensional least squares operation. So to perform this learned operation, HDLS-Net jointly estimates the learned operating context with the model-based correction using least squares. So to perform that, we start from the GNSS features and construct the model-based geometry matrix and residuals, as is the top block. Simultaneously, we also pass these features through a fully connected network for each satellite to produce learned values of these matrices as well as corrections. The model-based geometry matrix is concatenated with the learned matrix, while the model-based residuals are appended or added with the learned corrections, and the overall high-dimensional least squares optimization problem is then solved using the typical approaches. And from this, as an output, we get the model-based position and clock bias correction, as well as an output of the operating context. Next, I will talk about how this output from the hybrid module is combined with the sequential information using an LSTM. So to combine the outputs of the HDLS-Net, which are operating context and model-based corrections, we also need to provide information about how these different outputs are related to each other across times. So using the initial positions and clock bias values, we also construct relative pose features that contain this information and pass that to the LSTM to produce the final position corrections. These relative pose features consist of the transformation matrix between the NED coordinate frames between every two time steps. And this NED coordinate frame is based on the initial position at the time step, where the rotation is parameterized using the 6 degree of freedom representation, as is used for stability in previous learning-based approaches. Now I'll move on to the experiments. Our experimental data set consists of a simulated data set, which is used for being able to provide control settings for the initial validation of our approach. We use a simulated data set because it lets us generate diverse measurement errors in relatively short trajectories, which is difficult to obtain in real world. As we show next, this measurement data set that we construct in a simulated fashion is difficult to perform well for existing model-based approaches on. Future validation of our approach will incorporate real-world measurements as well for a more comprehensive evaluation. For our simulated data set, we use 5 randomly generated trajectories using the kinematic unicycle model, where we utilize 40 time steps per trajectory. These trajectories are generated in the NED frame of reference, where the origin is set to be the Durant building in Stanford University. The data set splits include 50% data, which was used for training, and the rest 50% was used for testing. The simulated data set contains pseudorange measurements, which have a 5-meter standard deviation. And we used 10 simulated satellites whose trajectory was determined using actual RANX data. We also apply an elevation mask of 5 degrees on these satellites. To each of the pseudorange measurements, apart from the standard deviation error, we apply a random bias, which has a mean between 20 to 100 meters with a standard deviation of 5 meters, which is added based on the satellite line of sight vector, as can be shown in the pictures on the right. These different and a different bias-inducing range of these line of sight vectors is chosen for each trajectory. For initializing the position, we initialize it uniformly in the range of plus minus 100 meters of the ground truth values. So here is the outline of our experiments and baselines. We compared the positioning performance of our model with other baselines that are trained on length 1 sequences, where the baselines used are the fully connected network, as well as the set transformer, which was developed for a previous learning-based approach. Uh, we also consider least squares as a model-based reference for perspective. Uh, in the first experiment, we use a non-sequential version of our model to have an apples-to-apples comparison with the baselines, since these baselines have been designed for snapshot settings. For this experiment, we evaluate the positioning performance of our models after they have been trained for few epochs, as well as after they have been trained for several epochs to show the data efficiency. Next, we compare the memory footprint of our models that have been trained, that has been trained for length of sequences with the baselines. And finally, we also evaluate this for longer sequences, where we evaluate the positioning performance as the length of the sequence changes in LSTM. So for our first experiments, we compared the positioning errors across the different learning-based baselines, as well as compared to the model-based reference. So we observed that after a few training epochs, for which we used 10 training epochs, HDLS-Net improves over the model-based baseline, which is least squares, and is therefore more data efficient, while the other learning-based approaches still underperform even the model-based baseline. However, we also observe that this data efficiency comes at a trade-off of the positioning performance when the models are led to train for longer periods of time, which in this case is 500 plus training epochs. So as we see, once the models have trained till convergence, the other learning-based baselines show smaller errors, even when all of them improve over model-based reference. In conclusion, HDLS-Net adapts faster and therefore is more data efficient, but still shows larger errors at convergence compared to other learning-based approaches. Another advantage of our proposed approach is that its memory efficiency, which we show by comparing the memory footprint of the different baselines using model parameters. As can be seen from this plot, fully connected networks require the most parameters, and they also scale with the number of satellites. So here, these plots have been generated for a fully connected network designed for 10 satellites, but increasing the number of satellites would increase the number of parameters even further. Compared to that, set transformer does not scale with the number of satellites, but still requires a significantly high number of parameters and therefore higher memory. Compared to both of these, HDLS-Net requires minimal parameters, which is less than 10 times the memory required by fully connected networks. Next, we compare the position, we extend the training process to sequential settings, where we compare the positioning performance of HDLS-Net when it is led to train for longer sequences. As we can see from this plot of the cumulative distribution error, as the length of the sequence increases and hence more sequential information is integrated, the positioning performance of our approach improves. Hence, the HLS-Net positioning errors decrease with increasing sequence length, and we see that it also saturates after a sequence length of 3. So in summary, we designed a novel hybrid neural network-based approach for GNSS positioning that combines the data and memory efficiency of model-based techniques, as well as the high-fidelity modeling capability and adaptability of learning-based techniques. The hybrid architecture combines measurement information both across different satellites as well as across time steps. And compared to learning-based approaches in simulations, our approach shows smaller positioning errors with fewer epochs of training and a smaller memory footprint, both of which show its efficiency. And compared to the least squares optimization, our approach shows improved positioning performance, showing that it can adapt to settings where the model does not extend to. With that, I would like to conclude this presentation. Thank you, and special thanks to all the NAB Lab members for their insightful discussion and feedback.